Okay. I made sure to actually remember to bring good chalk. Clean the board like I asked. And oh, okay. Oh, yeah. So it's only the important. Yeah.
I think it's Monday too. So I mean.
Yeah, because I previous class, which was almost 2 weeks ago, I asked Lisa to have him come in here instead. Oh man.
But I don't think that's.
Okay, so hopefully the rest of chapter 0, and so I'll hopefully I'll get through this stuff with a little bit of time left over, and nobody has any questions because you guys never do.
So are you saying we made?
Yeah, well, I wanted to make sure we just a little early because I'm a student. I'm seeing right at 4:30. So,
Oh, okay.
yeah, so we.
So you're saying you don't want me to ask questions? No, just kidding.
You already turned stuff in. Okay. The next batch of problems, I picked them out, but I haven't posted that yet for chapter 1 because I won't get to chapter 1 until.
You already did all the problems, and ones we haven't even done today.
You did the assigned homework.
Which problems? Should I put it on the site or ones in the notes? Because I haven't looked at it yet. Problems or something.
Yeah.
So we'll make you. Okay, so in today's notes, actually, have I posted those notes yet? I don't know if I. Okay, so yeah, I haven't posted today's notes yet because I do have more problems up on the site. If you go to the assignments page, I will post problems as I choose them. So again, if you go to the assignments page, you can see the rest of his chapter 0 problems. However, I've not covered that yet. So yes, you've done all the problems and everything you've actually covered.
Yeah.
So, but I'm gonna have homework due by the chapter. So, and because of we lost a day to the storm. That 5.
No, we even boarded our windows up because it was supposed to come straight for us. We got nothing. Rain. Nothing.
Yeah, because I was staying up late that night and I'm watching the weather that I got on weather.com and it says rain in view, rain and 2 and 2:15 and 3:30. It's like, oh, the heck with this. I'm going. That's not what I actually said, but edited for class.
As in the Nixon tapes, they would say expletive deleted.
But we still lost today because the university knee-jerk closed the campus. So these problems from chapters today will be due a week from today. Today, when I start covering chapter 1, I'll be starting to pile on more problems. And yeah, kind of a small selection of problems have solutions in the back, or not solutions, but really just answers, not written out solutions. But it's something. It's a little more than nothing. Okay, so finishing chapter 0, so 0.4 to 0.5. Okay, so I'm going to deal with a very important, very helpful inequality. Now, in the book, it's called the Schwarz inequality, but in many sources, it's known as the Cauchy-Schwarz inequality, and then in one book, it was actually called the Cauchy-Schwarz-Bunyakovsky inequality. But that thing is too long, so hardly anyone uses it. So,
but far more accurate.
Yes. So, unfortunately for Bunyakovsky. So, I guess Russians don't get the credit. Yeah. Even though they've probably come very big first. So let's suppose that if you have vectors x and y in Rn, so in that case, we're using the standard dot product, where you're just multiplying all the components, corresponding components together and adding them all up. you have a formula for the dot product, and that is it is the Euclidean length of x times the Euclidean length of y times the cosine of the angle between them. But the thing is, cosine has to be between -1 and 1. So that immediately leads to the absolute value of the inner product less than or equal to product of the magnitudes. Okay. Just from extreme cases of theta equal to 0 or this is for the standard inner product or dot product in Rn. Okay. But it actually holds more generally. So the Cauchy-Schwarz inequality holds for any inner product space. So then you have x and y, or actually, okay, yeah, same notation. In V, it still holds. Okay, and in this case, the absolute value is particularly necessary up here, but it's actually not necessary because the right side is. But what if this is a complex number, which can be for a complex inner product space? So we have to take the modulus to be able to compare it to the right side, which is always a real number. Okay. Now, what I'm going to do is I'm going to prove this from a case where V is a real inner product space. The case of a complex inner product space, it holds there too, is it's written out in the notes. It's just once you've seen a real case, then complex case isn't really all that interesting. Okay. Okay. So. So if I look at this vector, x minus t y, where t is some constant, and I look at the norm of it. Well, that's the inner product of itself. Now the norm, of course, is non-negative. So since the norm squared is the inner product with itself, okay. Now, in any proof involving inner products, this is something that happens very often. So it's a good idea to put this in your mental cache. It's good to know things. But if you have the inner product of something with itself, and that something is a sum or a difference, then it always breaks down like this. So we have the product of x with itself. Basically, you're foiling it out. Okay, so then we have and here I'm using the fact that the inner product, or for a real inner product space, is commutative. Because I have inner product of minus ty with x, and then here I have x inner product with ty. I can only combine those terms if it's commutative. So it's because it's real, I can do that. And then I have plus t squared. Here I'm using various inner properties of the inner product. Like I can pull constants out. I'm also using the linearity of the inner product. Whoops. Okay. The linearity of the inner product to be able to separate out these terms in the first place. But once again, we have inner product of various things with themselves. So that would be norm of x squared minus 2 inner product, x and y. And this is the very thing that I want to be less than or equal to something. And then t squared, y squared. Okay. Now, my questions so far?
Is it less or equal to?
Well, there's different ways of writing this. I'm saying equals because it is equal to this. And then that, so therefore this is also greater or equal to 0. Yeah. Okay. But I can see why I should say, oh, less than or equal to, but yeah. Okay. Now, this whole thing is a quadratic function of t. So think of this being this over it's describing a parabola. So this is your quadratic coefficient. Like if it's ax squared plus bx plus c. This is your a. This is your b, or the minus 2 times the inner product, and then that is your c. But it's a quadratic that is always greater than or equal to 0. So what can we say about the roots of this quadratic? What? I'm sorry.
They're all real.
Actually, we
Or
don't
you
know
say
that.
they're all greater than 0?
Well,
Oh, wait. It's greater than 0. They're all imaginary, right? Because they wouldn't even touch.
well, if it was strictly greater than 0, then yes, they would be
Oh,
imaginary.
there's only one.
There could be 1. Yeah, if this actually hits 0, then yes. But so that one root would be, what do we call that kind of root? If it's only 1, when it's a quadratic, though.
Oh my God. I teach this class. Y'all teach this class. What's the word that I'm looking for? Is it the multiplicity?
Yeah, it's
Okay, it's a
double.
double.
Yeah, okay.
I couldn't think of the multiplicity word.
Yeah, okay.
My bad.
Don't worry.
Okay. Well, hopefully she doesn't watch YouTube.
Oh. Well, I got the correct answer at the end.
Yeah.
Okay.
All right. So what that means is the discriminant, the b squared minus 4ac, has to be less than or equal to 0. Because from a quadratic formula, the only time you get 2 real roots is when a discriminant is strictly positive.
Yeah.
So it's equal to 0 for a double root, and then less than 0 to have these 2 imaginary roots. So let's fill in what the a, b, and c are. So this b comes from here. So we have minus 2 inner product of x and y. That whole thing is squared. Minus 4a is a coefficient of t squared. And then c is this, the constant term. All right, must be less than or equal to 0. So what happens is you get 4 absolute value inner product of x and y, because the subtle point, the square root of something squared is not that something, it's its absolute value. Okay, well, actually, when I take the square root, it will be. Sorry, I jumped ahead of myself. Okay, so I actually don't need the absolute value yet. Squared. Okay, but now 4's cancel. And now you take a square root of both sides, and that's where the absolute value comes in. And you get the Cauchy-Schwarz inequality. Okay. So it's nice to mix these properties and inner products with a little bit of Math 101. And then you get this result that's going to come in handy now and then. So any questions? All right. So that's one essential property that of norms and inner product spaces. And then another one, which can be proved using similar properties, and you're already familiar with it just from real numbers, is triangle inequality.
So t is a variable, right?
What?
T is a variable.
Yes. Yeah. Yeah. It's t. Yeah. T could be any real number. Now, in the complex case, you can't work with just x minus ty. You need an e to the I. You need a complex exponential in there, based on the complex argument of the inner product of x and y, and then this whole argument works again, because this needs to be a real number. That's for all of us to work. So that's discussed in the notes, which I'll be posting afterwards. Okay, triangle inequality. Okay, so that is that the norm of a sum is less than or equal to the sum of norms. Okay. So what we do here is start with the norm of x plus y squared. So that's the inner product of x plus y of itself. So what we would get when we FOIL it out is norm of x squared plus 2 inner product of x and y. So again, this is a real case. It would be similar for complex. Okay, plus norm of y squared. But the thing is, now we can use the Cauchy-Schwarz inequality. Oh, actually, this right here is equal. So this is equality right here. Now we go to less than or equal to. So inner product of x and y is less than or equal to norm of x times norm of y. Okay. And what we have on the right side, now a perfect square. Make sure this is still recording. Yeah. Okay. So that's less than or equal to. So I'm unfoiling, if you will. That. Because like a plus b squared, quantity squared is a squared plus 2ab plus b squared. As a result of replacing this. So now I can take the square root of both sides, and this falls out immediately. All right. So, nothing to it. Okay. Well, one page down. Okay. Now, so from this, from the inner product, for sort of general inner product space means to have orthogonality on a general inner product space. And this is based, this definition of orthogonality, even though it's for a general inner product space, is what happens in Rn is to motivate these definitions. So, as I wrote earlier, dot product is equal to magnitude of x times magnitude of y, norm of x, norm of y, times the cosine of y. So, equal to pi over 2, so that in other words, if the vectors x and y are perpendicular in dimensional space, so if x is, that means that the dot product is 0. So let's just use that to define orthogonality on a general inner product space. So we say that so inner product space I'll call V. So two vectors in any inner product space x and y are orthogonal if their inner product is 0, whatever that inner product may be. Now, that's just one definition I'll make. Another definition is if you have so set E1, E2 up to En vectors in this inner product space is an orthonormal set if the norm of each of these vectors, using whatever inner product, is equal to 1. So they're normalized. And they are orthogonal. So inner product of EI and EJ is equal to 0 if I is not equal to j. So really what we're saying is the inner product of EI and EJ is 0 if I is not equal to j. It's equal to 1 if I equals j. So we call them orthonormal because they're orthogonal and they're normalized. So it's very, very convenient to work with orthonormal sets if we can get them. Okay. And then the last part of the definition is if you have two subspaces of V, V1 and V2. So basically subsets of V that are themselves vector spaces, in other words, very closed under addition and scalar multiplication. So subspaces are orthogonal if you pick any vectors, one from V1 and one from V2, then those vectors are orthogonal. So in other words, every vector in one vector in the other subspace. Okay. All right. So examples of in L2. That's what we're going to be working with is okay. All right. And if we can express a function in terms of an orthonormal basis, that's for us. So we're working with orthonormal bases of one kind or another, pretty much all semester long. Now I'm not going to do every single example that's in the notes because tedious, but I'm there for all of them. Okay, first a very simple example. Suppose you're given a line in the plane, y equals mx plus b. Okay, so you can think of this line as having a direction vector. That would be just 1m. 1 unit, you travel m units with the slope in the y direction. So rise, run. It goes backwards. Right.
Not in my class.
Okay.
I had them, I think it was about a dozen times in the whole.
That's what I said in class today. I told parents, and I was like, and a bunch of y'all will switch us. But if you prove me wrong, that'd be cool. But they won't.
You fought a good fight.
At the end of the day, there's only so much.
Yeah.
Okay.
I had a student email me today and asked me if we were having class at a certain time today. I teach on Tuesday.
Okay.
I hope you wrote back yes.
No, I would be in trouble for that.
I wanted I didn't even know what to say.
So here's something, and you probably cover with great difficulty in 101. What is the slope of the perpendicular line to this one?
Negative whatever else.
Yeah. So
Opposite reciprocal. This is what it's called, guys. I taught it today. Thank you.
so that has a slope of minus 1 over m. So that would mean that the direction of that line would be 1 and minus 1 over m. Okay, so let's take the interproctivities. So we have 1m. Oh,
Negative 1.
this is I have a notation quandary here. Yeah, I should not have used angle brackets here. That's for the inner product. They're just vectors, so let's use parentheses there. Okay. All right. So dot product of 1m with 1 minus 1 over m. What do? You take corresponding components and you multiply them. And you add them all up. And hopefully even your 101 students can see that this is 0. No? Okay. I've always said, because once in a while it happens where regular faculty members need to teach 101 because we have so many sections and they all got to be staffed. And so in fact, I almost got assigned to teach 101.
This semester?
No, during my second year here.
Oh.
But there was a change after that. I think we didn't have as many grad students back then, and I think that's part of a push to get more. So, but I would say the first time they have me teach 101, that's the semester I get fired. So, okay. So, and sure enough, is what we expect because these directions would be orthogonal. That's because we chose the slope to be that way. And sure enough, those directions really are orthogonal. Okay. So for instance, like the line y equals x is orthogonal to the line y equals minus x. Okay. So that's first example. Okay. Now, so these functions will be of importance much later on when we study wavelets. You can use x here, not t in the notes. All right, so I define the function phi to be equal to 1 on the interval 0 to 1 and 0 otherwise. So it's a function that graph looks like this. And then I'll define the function psi. Oh, that should be nice. So that is equal to 1 from 0 to a half, minus 1 from 1/2 to 1, and then 0 otherwise. So that graph is in 3 pieces. So it's 0, then goes up to 1, then down to -1. Okay. All right. So this is a graph of phi, and that's a graph of psi. All right. So these are functions in L2 of if we just focus on 1. So these functions are certainly square integral because they're piecewise constant. So if you look at their inner product in L2, 0, 1. So that'll be our vector space. So then the integral of the psi will be conjugated, not its real value anyway. So because psi is piecewise defined, I need to break 0 to 1/2, and then from 0 to 1. So phi is equal to 1 on this interval, and psi is also equal to 1. And then from 1/2 to 1, phi is still equal to 1, and psi is equal to. Now, shortcut, anytime you're integrating a constant function on an interval, it's just the length of the interval times the constant. First integral evaluates to 1/2, and second integral evaluates to -1/2. So these functions. Okay, still recording. Are we? I can't really tell. Okay, yeah, it is. All right, so now I'm just looking at my screen looking stupid in the video, but whatever. Okay, so they are orthogonal in V. Now, if I had chosen like the whole real line, like L2 minus infinity to infinity, it would also be orthogonal because you'd just be tacking on the rest of the real line where these functions are 0 anyway. But if I had chosen a different interval, like maybe 0 to 1/2, they would not be orthogonal in L2 of 0 to 1/2 because we're both equal to 1 on that whole interval. There's nothing to cancel with. Okay, so when we get to the Haar Wavelets, which is in chapter 4, these functions generate all the Haar Wavelets. So that orthogonality will be very helpful to us then. And then one more example. Let's see. Okay. Ask me. Whoops. Yeah. Okay. I think it bugs me is like over here, like it's is equal to sine t, and g is equal to cos 2 of minus pi to pi. Okay. So now we take the inner product. So that would be an integral from minus pi to pi of f of t, g of t conjugate. So integral of sine t, cosine t. So what you can do is use double angle formula. Is equal to 1/2 sine 2t. Okay. How many of you probably forgotten all your trig identities from years years of disuse. Actually, when I was a grad student was when I realized I'd forgotten them and I needed them and I had to brush up. And now I can't forget them if I tried. So,
How did you brush up?
Wikipedia.
No, I mean, what did you do to remember them?
Oh yeah.
Yeah,
Why
I
do
mean,
you remember them so well now? Because you did it
Oh,
when you were older, probably.
Well, the thing is, like, it's not like we played like a role in my research or anything, but I think, so in other words, once I like what I do to keep them.
Okay.
Is that what you're asking?
Yeah.
Oh, okay. No, but because it kept coming up in classes.
So the secret of memorizing the trig identities is teaching a trig class.
Or a class that happens to use trig. For
I really
instance,
think that. Never in anything teach class.
yeah, that's why I'm a zillion times better mathematician now than even when I was hired. So Cal 2 uses trig constantly
Oh yeah.
for all the different integration rules. So that's a really good one. They're certainly teaching certain low-level classes. Okay, like not 102, because 102 doesn't use trig, but yeah, some of you will be assigned to teach 103. That's our trig class. Like could be on the spring. Generally, you guys teach non-zone classes in the spring because we just don't need as many. Because chances are, like Dr. Bullock or his sons or Mr. Stanford can cover most of them. So your time will come. So and actually, once in a while in research, certain trig identities can come about. It just depends. Okay, so now this can be integrated directly, and what you get is minus cosine of 2t over 4 with limits minus pi and pi. But so what you get is cosine of plus or minus 2 pi. Well, cosine of plus or minus 2 pi is always equal to 1. But because you're subtracting the values at the upper and lower limits, it will cancel out and you will get 0. Well, the other way this could have been integrated using substitution, like u equals sine t, and then this is your du. So that also would have worked. Anyway, the point is, these functions are orthogonal. And as will be seen later, like in chapter 1, when we get to Fourier series, you can show just by working out the integrals directly that these functions, that 1 over square root of pi sine nt, 1 over square root of pi cosine nt, where n is all the positive integers, are orthonormal. Okay. So here I did is sine t and cosine t, but if I had sine nt and cosine nt, you can work the integral in a similar manner, and it turns out you still get 0. Also, sines like sine nt with different integers, those are orthogonal to each other, and same with cosines. The only thing we're missing here is if n is equal to 0, we get a constant function. That also is orthogonal to these, but it has to be normalized differently. So this is what we will use with Fourier series to be able to compute the coefficients using the fact that they're orthogonal simplifies the process. Okay. 2 pages down. So in fact, how we expand a function in an orthonormal basis in general, whether it's like other ones, works out quite nicely. Okay. So supposing the orthonormal basis for some subspace that I'll call V naught, a product space. And you let, okay, give me these letters, I need to reinforce that they're uppercase. Okay. Let's suppose I choose an arbitrary vector V that's in the subspace V naught. So what I want to do is, because it's in the subspace, and E1, E2 to En are a basis for the subspace, they can describe all vectors in the subspace. So we know that V is some linear combination of the E1 of the E's, and the coefficients are the alphas. So the question is, how do we get the alphas? Well, it turns out it's quite easy to do. So what I'm going to do to get the coefficients, I can take the inner product of both sides with one of these vectors from a basis. So I'll take the inner product of EK. Now, on the right side, I can use the linearity of the inner product. So I can pull out the sum and the constants, and left with inner product of EJ with EK. But the E's are orthonormal. So all of these terms go away, except when J is equal to K, in which case this inner product is equal to 1. So what's left? Alpha K. So that's the coefficient right there. So I can write this as V with EK, EK. So when you have an orthonormal basis, it's very easy to get the coefficients of some vector in that basis. It's just the inner product. And so the nice thing is you can compute all the coefficients independently of one another. Very helpful. So you can compute them in parallel, for instance. Okay. All right. And if the suppose the basis is infinite, this also holds. Although whether you actually have equality in this case, when it's an infinite basis, it depends on the particular vector space you're dealing with. Like you need the vector space to be complete, for instance. Then you actually get, in other words, all of these kind of, now you have an infinite series, it doesn't converge. Okay. But mostly in this class we're working with like finite bases because we're interested in practical computation. Okay. So here I talked about a case where V is in the subspace, and now we know how to get the coefficients. But now suppose that V is not in the subspace. It's any vector in the larger vector space. How can we at least approximate V by something that's in the subspace? And that's where we get into orthogonal projection, also known as best approximation. Okay, so now suppose so V naught is some subspace of V is an n-dimensional subspace. And I point out that n is finite. and I let little v be any vector in the whole vector space, the whole inner product space, not just v naught. So if I define this vector v naught to be a sum of inner product of v with all my basis vectors multiplied by ej. So it's the same expansion as over there. Oh, I just realized I goofed earlier. In this sum, v should be j's. Just because I'm summing over j. Okay. So what we have here is I'm taking in product of v with all the members of my basis. So once again, v naught has an orthonormal basis d1 up to en. So this vector v naught is the orthogonal projection of a vector v onto the subspace v naught. And so properties that v naught has is that, first of all, the error in this approximation, v minus v naught, is less than or equal to v minus u for all u in v naught. So in other words, v naught is closer to v than any other vector in the subspace. So besides being called the orthogonal projection, it's also called the best approximation of v in v naught.
I'm still thinking about this. Maybe I'm lost. I don't know. This v equals the summation of aj ej.
Yeah.
Equals the summation of inner product of v ej. Does that mean the inner product of v ej is equal to aj?
Yeah.
Okay. Wait. Does it say again? Inner product of
aj.
The V1 EJ, the summation, he's asking if that's the same thing as the alpha J.
Oh, yeah. Yeah, this is alpha j.
That's alpha j.
Look at what's underneath it.
Yeah, because that's what it's done here.
Okay.
VEK is alpha k.
Okay, yes.
Right. Okay. Yeah, I guess I don't feel as much because I'm moving around.
Yeah.
But yeah. Okay, is that? Okay.
Yeah, I goes up a little bit.
Okay. All right, so that's one property of the orthogonal projection. It's the best approximation. Is that the error v minus v naught orthogonal to u for all u and v naught. So in other words, the error is orthogonal to the subspace you're projecting onto. All right. Now, I'm going to give a very simple example for a simple vector space. Your vector space is just so the idea is I have some vector. This will be v, and I want the best approximation of v that's contained within this plane. So what I would do is I would drop a perpendicular. So this vector right here, contained within this plane. So the plane, that's V naught. So it would have a two-dimensional, so V naught is a two-dimensional subspace of the three-dimensional space R3. Okay. You were doing so well.
I know.
Yeah, well, you lasted for more than half the class, so that's cool. So this vector right here is V naught. And this vector right here is wait.
Where's U? Just a different one?
Well,
Vector V?
yeah, use any vector in this plane, for instance. Yeah. Okay, actually, since I put the arrow. Okay, I need to put the arrow on the other side. Okay. So that's V minus V naught. So this is perpendicular to the plane. It's in the same direction as if it's normal to the plane. Because if I choose any other vector in this plane, the distance from that vector, like if I choose something else over here, this is going to be further away from the tip of V than V naught. So V naught is the best approximation you can get. All right. So in fact, I have a theorem in the notes that this is true if and only if this is true. And I won't go for proof of that because it looks like I'm already behind. But the thing is, it actually uses the same properties of the inner product as I used earlier when proving like the Cauchy-Schwarz inequality, the triangle inequality. So the same kind of manipulations. So those properties certainly come in handy. All right. And I jumped ahead of myself and already gave a formula for projection. That hadn't actually come up in the notes yet, but okay. So I'm not as behind as I thought. So that's good. Okay. Because the thing is, if you start out with this, actually, these properties are a lot easier to prove when you already have this in hand. So, okay, which is actually what I did in my textbook. Okay, so, all right, so now I'll do a couple examples involving orthogonal projections. I guess now I have another reason to end early.
Say what now?
Now I have another reason to end early.
What?
To end your suffering.
Yeah.
Or everyone else is suffering.
I'm sorry.
Okay. All right. So let's suppose our space, our vector space, is just L2, minus pi to pi, and my subspace is a span of these functions, cosine and sine. Now span, that's this linear algebra term. That's a set of all linear combinations of cosine and sine. So on an orthonormal basis. Now cosine and sine are orthogonal. I showed that earlier.
Yeah.
But I need to normalize them. So orthonormal. But that also equal to the span of this set. Cosine over the square root of pi and sine over square root of pi. So this is E1 and that is E2. So orthonormal basis. So if I let f of x equal x. So this is playing the role of my little vector v approximating. So I want to approximate x by the linear combination of cosine and sine. So f naught is the projection of f onto v naught. So that would just be inner product of f of E1 times E1 plus inner product of f of E2 times E2. So that's the formula over there applied to this two-dimensional subspace. So, okay. Now, so what I would need to do is compute these inner products. So I actually need to evaluate the integrals. So this would be integral from minus pi to pi, x cosine x dx, and then we have a 1 over square root of pi out here. And this one would be similar. It would be 1 over square root of pi integral of x sine x. Now, what would we have to use to integrate those?
Wait, where did the x come from? X times cosine x.
There.
Oh, okay.
It's a function we're taking the inner product with.
I got you. Now say what again? What do we have to do to
Yeah, what technique would we have to use to evaluate integrals like these?
parts?
Yeah, integration by parts. Well, we're not going to do that here.
We'll
Fortunately,
just trust you.
fortunately for cosine, we actually don't have to, because if you look at f of x equal x on minus pi to pi, that looks like this, and cosine looks like this. Now, this is something we'll actually get into later, but even and odd functions. What kind of function is x, even or odd?
It is.
Did someone else say over here?
It's odd.
Yeah, odd. And cosine is even. Now, unlike multiplication, an even function has an odd
Did you see
function.
the chalk come out?
You see his chalk just went.
Wow.
Well, it's from your hand. It's not y'all talking about.
Okay. Yeah. Oh, that's a relief. What are we gonna find it in my lungs when I'm dead? Okay. So unlike regular multiplication numbers, even function times an odd function is an odd function. So it's more like the rules of addition, actually. So this function is odd. The integral of an odd function over a symmetric interval like minus pi to pi is 0. So this makes no contribution. Only this does. And if you were to evaluate that integral, you would get 2 sine x. So, okay, so if I graph that, 2 sine x, all right, so I'll get rid of cosine. So that's going to look something like that. So you can see if you scale it right, you can get a semi-decent approximation of x, because the sine x and x are both odd functions, so you want them to have that kind of symmetry. So that is the best approximation. So that's your f naught. So that's the best approximation of x by a combination of sine and cosine. It's turned out, for this particular case, you only needed sine. Okay. Actually, yeah, I'll do the other example. Involving these functions I introduced earlier for wavelets. So phi of x is equal to 1 on 0, 1. And psi of x is equal to 1 on 0 to 1 half and minus 1 on 1 half to 1. And 0 otherwise. So, and I'm going to let fx again. So we're working on L2 0, 1. I'm still getting those crank calls for a phony IR. It's using one of the Windows voices.
Just answer like Hattiesburg Police Department.
Yeah. Okay, so I want the best approximation of this by a combination of these functions. Now, it turns out that these are normal because, so for example, the norm of psi squared is the integral from 0 to 1 psi of x dx squared. But if you square this, it's just 1. And so these are already orthonormal. My E1 and psi is my E2. So my best approximation of f of x equals x, again, is equal to inner pi times phi plus inner product of f of psi times psi. So these inner products are my coefficients. So I'd have the integral from 0 to 1 of x times phi plus integral from 0 to 1 of x times 1 plus integral from 1/2 to 1 of x times minus 1 all times psi. So now I can evaluate these integrals, and what I get is this one will turn out to be, and then this integral will turn out to be minus 1/4. Okay. I have x squared over 2 from 0 to 1/2, and then I have x squared over 2, or minus x squared over 2 from 1/2 to 1. So we work out.
1/2 or negative 1/2?
What?
Negative 1/2.
No, not.
Look up. Up.
Oh, that's wrong.
Up.
Good catch. Okay. All right. Yeah, we're on 0 to 1, the interval for defining these things. Okay.
I think.
What?
Is that one phi? The top one? No, the norm of. Yeah. Is this psi or phi? Is it omega or?
Oh, but this is psi. I only did that one. If you did phi, you have the same thing. Okay, but yeah, this is what's more interesting. Okay, now, but the thing is, so this is equal to. Now, what is it actually equal to as a function of x? So this is equal to 1/2 minus 1/4 from, so 1/4 for x between 0 and 1/2. But now, suppose x is between 1/2 and 1. We get 1/2 from here, and then minus 1/4 times minus 1. So they add together, so you get 3/4 for x between 1/2 and 1. Okay. Now this seems strange until you graph it. So here's my function I'm approximating. This is x. So from 0 to 1/2, I get 1/4. And from 1/2 to 1, I get 3/4. So keep in mind, you're trying to approximate x by a function that is constant from 0 to 1/2 and constant again from 1/2 to 1. And sure enough, it takes the average values. It's a poorly drawn graph, but you get the idea. Okay. So for a piecewise constant function that has very limited capacity to approximate things, it actually does a pretty good job. And that's the best combination of constants that you can hope for to approximate x. So that's the orthogonal projection. Okay. All right. So questions about this example? Okay. Now, we'll say a few words about orthogonal complements. Okay. The definition's right here on that previous page. Okay. So, suppose these naught is some subspace of V. Okay, so this subspace, V naught, is called, we read it as V naught perp, because of a perpendicular symbol, is the orthogonal complement of V naught. And how we define it, V naught is equal to the set of all vectors in V such that inner product of V and W is 0 for all W in V naught. So in other words, whoops, forgot to complement. Okay. So the orthogonal complement is a set of all vectors in the entire vector space, V, that are orthogonal to every vector in V naught. So, like a simple example, let V be equal to R3, and V naught is a span of these vectors, 1, 0, 1, 0. So in other words, all vectors have Y component they want, but the Z component must be 0. So the orthogonal complement is a span of 0, 0, 1. So we basically, you're partitioning a vector space into some subspace of your choosing, and then all vectors that are orthogonal to that subspace. And that goes into the orthogonal complement. So right, V is equal to, we have this funny plus in the circle here, V naught perp. This is called a direct sum. So what that means is, you have a direct sum when any vector in V can be written as a vector in V naught plus a vector in V naught perp, but there's only one way to decompose. So the decomposition has to be unique. So that's what it means when you have a direct sum. So in a sense, they're kind of like geometrically non-overlapping subspaces. Okay. So in fact, what we can say is, so one theorem we have about orthogonal complements, that if we have any vector in V, we have this unique decomposition where V naught is in the subspace, capital V naught, and V1 is in V naught perp. So every vector in the inner product space has a unique decomposition into the sum of a vector from whatever subspace you're considering and its orthogonal complement. And in fact, we know what V naught is already. That's the orthogonal projection. Onto V naught subspace. And this is just the rest of it. It's like the error. So you can think of V. So this part is the approximation of V by a vector in V naught. This is the error. So together they give you V exact. Okay. Oh, all right. All right, in fact, I'll go ahead and do an example from R3. So V is R3, and my dimension 2. Oh, I might have a mistake. Check. Oh, yes, I do. I'll have to fix that. So my orthonormal basis from subspace is square root of 21, 1 minus, and the number vector is 1 over square root of 6, 2, 1, minus 1. I forgot the square root of my notes. Okay, so I let V be any vector in R3, this x, y, z. Then call this E1, and I'll call this vector E2. So my best approximation, so V naught is a projection of V onto V naught. So that's going to be inner product of V with E1 times E1 plus inner product of V with E2 times E2. So my inner product would be, all right, so x times 2z over the square times this vector, 1 minus 4 minus 2 over square root of 21. And then the inner product with the other vector would be 2x plus y minus z over square times the vector 2 over square root of 6. Okay. And what I can do, of course, I can combine these square roots together, so I just have 21 in the denominator here, and then 6 in the notes. So for whatever x, y, this vector, I could simplify this, of course, but that'd be a nasty fraction, or 3 nasty fractions. I'm not going to. But it's going to be some combination, all the coefficients, all the components will be various linear combinations of x, y, and z.
I have a question.
Yeah.
Why did you actually write E1 here? That's probably because it was piecewise and not for phi or psi. You just wrote phi or psi for the E1 and E2, but is that because they were piecewise?
I could have labeled them E1 and E2. That probably would have been a good idea in retrospect. Yeah. So I guess I did it because they were already orthonormal, as it's given. But yeah, to relate to everything else, yes, they're E1 and E2. Okay. All right. Now, what about the orthogonal complement? Well, this is R3, so this is dimension 2. The orthogonal complement has the only dimension left, dimension 1. So it's all multiples of a vector that is orthogonal to both of these. In R3, how do you get it in vectors?
The dot product.
Not dot product, but different kind of product. Cross product. Yeah. So V naught perp
It's Monday.
is a span of 2, 1, minus 3 for square root of 14. So it's 1 is with E3 times E3. So that would be inner product of this with x, y, z, 2x minus y plus 3z, all over 14 times 2 minus 1, 3. So any x, y, z breaks down into the sum of this vector plus this vector. So if this is the best approximation in this two-dimensional subspace, this is what's left. And if you wrote out all of this, you would see that this plus this really would equal x, y, z.
So how do you multiply that?
Okay, so you combine square roots. So here, this is just a coefficient, and then you have to multiply that by each of the components. So it'll actually be kind of messy. So you would get something like,
So you would multiply the coefficients by each component.
yes. So I'd have first component of this vector would be x minus 4y minus 2z over 21. Second component would be all that times minus 4. And third component would be all that times minus 2.
Okay.
And then you have to add corresponding components of that vector to this one. So you can see why I'm not doing it.
I really hope that's not a homework problem.
Oh no, I'm sure there's something worse there. But I don't remember, but yeah.
Okay, x, y is a that means the same like x, y is a.
Yeah.
Okay, so that the vector 1, -4, -2.
Yeah.
Is the same like I, J, K.
Yeah.
So when you are multiplying, are there any problem with like perpendiculars, like x to?
Oh, is it? No, but the only multiplication going on here is scalar multiplication.
Okay.
So you're just altering the length of a vector.
Okay.
Yeah, and then ordinary vector addition. Okay, where are we at? Okay. Well, getting close to the end, but okay. One last theorem. It's actually a very important algorithm. Gram-Schmidt orthogonalization. Well, some students like to have a vulgar name. But I guess it's the best approximation in some subspace. Okay. So Gram-Schmidt orthogonalization. Okay. You're given V naught subspace of V. And I'm in the right subspace. And you have V1, V2 up to Vn. For V naught. Now, I emphasize here, V naught can be, any naught. It does not have to be, so it's generally not an orthogonal basis that's convenient to come up with. Okay. So what I do is, if I define E1 to be, and then I define each vector Wj to be Vj minus the sum from 0 to j minus 1 of inner product of Vj with Ek times Ek, right? And then I define Ej to be Wj normalized. Okay. Then E1, E2 up to En is an orthonormal basis for V naught. Now, Gram-Schmidt is often introduced first time in a linear algebra class, where you're given the columns of a matrix, and you want to come up with a set of orthonormal columns that span the same space. That's actually foundation of a QR factorization. You took 610 already, didn't you? Okay, yeah, it probably came up there. Okay. So, given any set of linearly independent vectors, at least, we have a way to generate orthonormal vectors from them. And that's what this Gram-Schmidt process does. So for first vector, you just take the first given one and normalize it. What you do here after that is you take each new vector and orthogonalize it against be previous orthonormal vectors that you've generated already. And as you go, as you're orthogonalized against all the previous ones, you get a vector that is orthogonal to your basis, but it's not normalized, so you normalize it. Okay, so that's Graham-Schmidt. So actually, that means I've covered everything. Yeah. So, and thus ends chapter 0.
Serious thing all.
Yeah. So we start the real stuff on Wednesday.
But part of the depressing thing is that usually people have felt like they've finished chapter 0 by the time they open the book.
Yeah, most of the time, yeah.
Yeah.
Fix those a little bit, and I'll post them tonight or next couple hours.